All right, let's get started. Here's hoping the recording works out. I opened my backpack and my mic cable was like totally bent, but seems to be working. I guess we'll see. Okay. What's due today? Something big is due today. Assignment 1. Yeah, it's got to be an assignment, given that everything in this course that is graded is just an assignment. So yes, assignment 1 is due today. Don't forget to get that in. Reminder about the late policy. You can submit assignments up to 2 days late at the very most, and you do that by using grace days. You all have 3 grace days, because everybody starts out with 3. You can use them however you'd like. If you submit an assignment between 0 and 24 hours late, that uses 1 grace day. If you submit it between 24 and 48 hours late, that uses 2 grace days. You can't submit anything more than 2 days late, even if you have all 3 of your grace days remaining. So just keep that in mind. I don't recommend using grace days for this assignment. Honestly, like assignment 3, small shell, that's probably the one you'll want to save your grace days for, but it's up to you, of course. Okay. Question?
But like, isn't the assignment 1 when there's no submission, right? Is it not just like you push it to GitHub?
Yes, well that is how you submit. Push it to GitHub. But push it to GitHub before the end of day today.
Right.
Yeah. Okay, good. Other questions? Yeah, by the way, the TAs can see like your commit timestamps. That's how they're going to know that you turned it in on time. Yeah. Okay. So today, we're going to start with fprintf because I've covered file input, but I haven't covered file output. So we're going to start with that, but it'll be very quick because it's very easy. Then we're going to talk about sort of old school file input and output. So we've been using the newfangled Studio.h stuff. So like fopen, fclose, fgetS, getline, things like that. It turns out there's a harder way to do a file I/O in C. It's using like the C standard library stuff that's not from the POSIX Unix standard. No, other way around. It's using the stuff from the POSIX Unix standard, not from the Studio.h. But this stuff is harder, but you sometimes need it, and so we are going to cover that. Then we're going to cover more details about like creating files, but also like creating directories with certain permissions and navigating directory trees, and then you'll be ready for assignment 2. Which, by the way, does anybody know when assignment 2 is due? Next Thursday. Very good. So assignment 2 is due next Thursday. It's a week and a half or so from today. So you don't have a full 2 weeks to work on assignment 2. You just have like a week and a half or so. But by end of day today, you should have all the knowledge you need to complete it, I think. Okay. Questions or comments before we get started? Yeah.
Do you know how many assignments we're going to have over the term?
Yeah, there's 5. So assignment 1 is due today. Assignment 2 is due next Thursday. So Thursday of week 5. Assignment 3, small shell, that's going to be due Thursday of week 7. So you'll have 2 weeks to do small shell. And then after that, I think it just goes like Thursday of week 9, and then probably like Wednesday of finals week or something like that for the last one. Maybe even like Tuesday of finals week for the last one. I'm not sure. The last one, we call it the final project so that we can make it due during finals week, but it's really just another assignment. Yeah, there's nothing fancy about it. Remember, there's no final exam for this course though. Other questions? Okay, let's get started. So file output, it starts the same as file input. You create a file pointer to sort of handle the file stream. My file. You initialize it to an fopen call. As always, there's 2 arguments here. The first argument is the path to the file that you want to open. I don't think I said this, but if you supply a relative path to this for this first argument, for this C string, it's relative to the working directory at the time the program is executed. And so if you execute your program from within a certain folder, and then there's an fopen call within that program that opens a file at a relative path, it will be within the directory that you're in when you run the program. It's not the directory that the C code is contained in, like the C source code. It's not even necessarily the directory that the executable is in. It's the directory that your shell is in when you run the executable. Okay? And so maybe I open, I don't know, output.txt, something uncreative. Okay. For the second argument here, previously we supplied an R for read, if we wanted to read data from a file. Here I want to write data to a file. And so I've kind of got 2 popular options. I could supply a W, W stands for write. It's for writing data out to a file. There's also an A. A stands for append. If you use the W open mode, it will open the file for writing, but it will truncate its contents. So what that means is if this file already exists, this will open that file, so that way we can write data into it, but it will erase the current contents of the file and sort of restart writing it from scratch. So this kind of deletes it and writes it from scratch. If you want to add more data to the end of the file, which is very common if like you're appending to like a log file or something like that, you would use A instead of W. A stands for append. So we open it for appending. I can demonstrate both of these. Let's start with W for truncate, right? Okay, so we have our file stream. Before I forget, let's call fclose down here to close it, clear up those resources. Okay, suppose I want to write data to this file. If we wanted to read data from a file, we talked about fgetS and we talked about getLine. Those were the two main ones. There's also fscanf, which works just like scanf, but lets you read from like arbitrary file streams, including standard input, but also other file streams. If you want to write data to a file, there's a nice function for doing it. It's fprintf, right? So printf, this is how you like write data to the terminal, right? It stands for print formatted, for printing formatted text. fprintf is the same thing. It just has a little f at the beginning, and it takes an additional argument. So with printf, the first argument is the format string, right? Maybe I want to write an integer followed by a space, followed by a double that's written to 2 decimal places, followed by a new line. So I'd supply my format specifiers, and I'd supply some values. Let's see, the integer is maybe -12. And then the double value is maybe 3.141592. It will be written to just 2 decimal places, so that's 3.14, and then it will put a new line, right? This is how we would call regular printf, and that would print this data to the terminal. If I want to print it to a file, I call fprintf, and there's an additional argument, and I believe it's the first argument, because that's the only thing that would really make sense, and it would be the file stream, my file, right? Let's hope that's right. If it's not, I'll have to look at the man pages, but I'm pretty sure that's right.
It feels right that it would be first.
It would have to be first. Well, it'd have to be first because all these arguments are variadic arguments, and this one has to be special. Yeah. So yeah, it would be crazy if this wasn't it. This should be it. You might have guessed that this would be equivalent to just calling printf, right? Standard out is a file stream that points to standard output, which lets you write data to the terminal. And so if I use fprintf, for the first argument, you specify your file stream that you want to write data to. If you supply standard out, it's a built-in, but it's like a handle on a file stream pointer for standard output. Then this writes to the file stream standard out, which is just what printf does. The nice thing about this, though, is that you could also supply something like standard error. So you could write data to standard error instead of standard output. There might be other ways to do that, too. But in our case, I want to write it to our file. So I put my file. And that should be it. Let's run it and see. All right. I run it. Now, I should have a file called output.txt, which previously didn't exist. And I look at it. Here it is. There's our -12. There's our, well, I don't think my format specifier was right. Studio right. %lf point, %.2, yeah, it goes in the front. %.2 lf, there we go. Run it again, GCC, studio right, run it. Output text, there it is, there we go. That's what it's supposed to look like. So yeah, file output works exactly the same as standard output. You just call fprintf instead of printf, and then for the first argument, you just put your file stream pointer. And that file stream pointer is given to you by fopen, and you close it with fclose. But besides that, it's the same. Okay. Good. Questions on that? Okay, good. Now you know how to do file output in C. Pretty easy. Let's move on. So I think we've basically covered all of this stuff. I skipped some of it that wasn't super important. I skipped fread, fwrite, fseek. I'll just give you a basic rundown of what these things do. Fread, this is similar to fgetS and getLine in the sense that it reads data from a given input file stream, like a file stream that's open for reading. The one difference is that fread is designed to read like bytes, like a certain number of bytes at a time, like just bytes of data, whereas fgetS and getLine are used to read like string data. So these functions, getLine and fgetS, these are useful for reading text files, especially if you want to read like a whole line at a time from a text file. That's what fgetS and getLine are designed to do. Fread is you've just got some sort of data file, maybe it's a text file, and each character you want to read as a byte, and sort of interpret it as, through its ASCII code or whatever. But fread could also be useful for reading like non-text files, like binary written files, files that are just like serialized into some sort of byte code or something like that. You could use fread for that. Same with fwrite. It's also like fprintf, but instead of printing or writing text, like formatted text, it's used to write bytes. Now, an interesting thing is that in C, there is no type called byte. There's int, there's double, there's char, there's float. There's no byte type. The way people usually represent bytes in C is with unsigned chars. So char stands for character, right?
I found out that last night. Discovering that there's a byte order mark at the front of the CSV file.
Oh, really?
Not that it matters to parse the first line, but I was doing it for fun.
Oh, that's interesting. That's interesting. I didn't know that. Okay, but yeah, it probably doesn't matter if you're just reading the dummy line away. Yeah. Okay, so yeah, char stands for character. The one guarantee about sizes in C, sizes of types, this is basically the only guarantee besides relational guarantees, but the one absolute guarantee is that chars are always exactly 1 byte in size. Usually a char is a signed type though, which means they can be positive and they can be negative. So very commonly a char value, it's a character, but it's represented as like an integer ASCII code. And usually that integer stored within your char variable could be anywhere from negative 128 to positive 127. If you want to represent bytes in C, you very commonly want them to be unsigned. It doesn't really matter. I guess it just depends on how you're working with it. But usually if you're trying to represent like, bytes as like streams of bits, and you want to just think of them in terms of like zeros and ones, you usually don't want to have to think about like the sign bit at the beginning in this weird binary representation.
A lot of F's at the beginning of the...
Yeah, you got to be careful. And so we usually use unsigned char. It's not called byte, but it's sort of like a byte. There are some other things that people do. There's uint8t, which is unsigned integer, unsigned integer 8-bit, right? Yeah, so you could use that to represent a byte. Some people do that. Okay, but either way, you would create like arrays of these things and then read into them with fread and write them out using fwrite. That's sort of how those functions would work. There's also fseek. Fseek works similar to lseek, which we'll talk about soon. It's just used on, it's part of the like studio.h newfangled file IO in C, part of the C standard library instead of the POSIX Unix standard. And so we'll talk about lseek soon. fseek does the same thing basically. Okay, there's a few others that aren't even on here like ftel. We talked about feof. ferror and clear error are used for error handling. You can look them up if you want. Good, this last thing, sprintf, really doesn't have anything to do with file IO, but it can be really helpful when you're like trying to parse data from files. In fact, maybe some of you have already used this in assignment 1. Does anybody know what sprintf does?
It does print a string.
Yeah, into a string. And so printf is used to write formatted text into standard output, like into the terminal. fprintf is used to write formatted text into a file. That's what the F stands for. sprintf is used to write formatted text into a string. And so you've got a character buffer, like a character array, and you want to construct a string with a bunch of formatted data in it. Maybe you've got some numbers, maybe you've got some, like some integers, maybe you've got some doubles, and you want to sort of combine them into a string with nice formatting. You can use sprintf, and it has a very similar interface to printf and fprintf. But rather than writing that text into a file, it writes it directly into a character array and sort of constructs a C string in place to represent that formatted text. It's pretty nice.
We would need that in the assignment.
I don't know. I've seen people use it. I don't remember what for, but there are good reasons. Either way, okay. I think it'll be really useful for assignment 2. Yeah, for constructing like the file names. Okay, very good. Let's move on. Let's talk about the old school. People still use this stuff all the time, but Okay, but we'll talk about it. So we've covered sort of the easy way to do file I/O in C, like fopen, fclose, fprintf, fgets, getline, these sorts of things. There's a harder way to do file I/O in C, and so you might be wondering, why would we use these functions if the other functions are easier to use? And the answer is that these functions, they're harder to use. It's a more complicated interface, but they give you a lot more control over how the reading is done, how the writing is done. Similar to fread and fwrite, these functions are used to like read and write like arrays of bytes rather than writing, like strictly like formatted text and things like that. And so you have a little bit more control over how they work. Yeah, they're also pretty performant. So if you need things to be really, really fast and really memory efficient, you would often use these things instead of fread, fwrite, or fgets, or getline, and things like that. Okay, so let's talk about them. These functions are not provided by studio.h. They're provided by a different header file. Actually, I think a couple different header files. Okay, let me create a new file for this. Maybe, actually, I think I have one, read.c. There we go. Okay, if you want to use these functions instead, open, close, read, write, else, seek, the sort of lower level file I/O functions in C, you should include at least these two header files. So these things are part of the POSIX Unix standard, and so you have to include unistd.h, which isn't going to be available to you on all platforms, but it will be available to you on like StarNix systems, like the engineering servers, like the OS1 server. So you have to include that. And then you should also include this thing fcntl.h. I think it stands for file control or something like that.
The first one, Unix standard.
I think so. I could be wrong. But yeah, some of these functions are provided by Unistandard. Some of them are provided by fcontrol. So you have to include both of them. Okay. The first step, as always, is to open your file. And the last step, as always, is to close your file. Rather than using fopen and fclose, we're using these lower level functions. The sort of analogies are open and close. These functions are literally just called open and close, right? And so there's the open function, there's the close function. And I want to call the open function at the beginning, the close function at the end. I'll get to the interfaces in a second. First, the return type of the open function. Rather than returning a file pointer, like a file stream handle via a file pointer, my file gets open, something like that, the open function returns an integer. And yes, it literally is integer. It's not like size t or anything like that. It's integer. I called it FD. The reason I called it FD is because FD stands for file descriptor. Okay. So on StarNix systems, every process, which as a friendly reminder is like a running instance of a program. So when you start running a program, a process is created to sort of execute that program. Every process has something called a file descriptor table. So I'm going to write FD table for short. File descriptor table. The file descriptor table basically has two columns. This is one way of thinking about it. I'm going to try to simplify it a little bit, but here's more or less how it goes. The left column is the file descriptor itself, which is an integer. Right? The file descriptor, it's an integer. And then the right column is a pointer that points more or less to a file. There are more layers of indirection. It technically points to a different entry in a global file descriptor table, but it doesn't really matter. It basically points to a file on disk. That's one way you can think about it. So for example, there's FD0, there's FD1, there's FD2. These three file descriptors are actually special, 0, 1, and 2. Most files have, actually I think all files that you ever manually open with open or even fopen, they all have file descriptors, but their file descriptors will always be greater than 2 because 0, 1, and 2 are reserved. They're reserved. What are they reserved for? What are the three special file streams?
One of them is standard in, standard error, and const, or standard input.
Yep, standard in, standard out, and standard error, right? These are three special file streams. They also need file descriptors. They're not technically files, like there are sort of file handles for them, but they behave a lot like files. And so they get file descriptors. 0, 1, and 2 are typically reserved for standard input, standard output, and standard error. I don't remember the order. I think 0's
first.
I think it is first. I think.
remember 1 and 2 are used in redirection.
Yeah, I'm pretty sure 0 is standard in. Let's see.
Because when you use redirection and you need to specify to merge the standard in and out.
You dupe to
one and
0.
two.
Yeah. Oh, yes, exactly. Yeah, when you redirect standard output to standard error, you go arrow, or 1 arrow and 2. So yeah, 1 is standard output, 2 is standard error, 0 is standard in. Okay, and so that's sort of the left column. And then of course, anytime you open a file via the open function, or via the fopen function, or any other function that sort of opens a file in some way or another, a new file descriptor is created to sort of represent that the handle on that file. And so if I call the open function and I open hello.txt, then maybe it creates a new file descriptor 3 to sort of point to hello.txt, right? txt, something like that. 0 standard in, 1 is standard out,
Surprised they didn't just do pointers to pointers.
2 is standard error. They do. I'm simplifying this. They do
Why
pointers to
the
pointers.
file descriptors are integers instead of pointers?
I don't know. Because it goes in this process table and it just uses integers to represent it. Okay.
Probably used a smaller size.
Okay, so the right column is it's a pointer to a file. Technically, it's a pointer to something called a file description. So each one of these will point to its own little file description. A file description contains a few pieces of information in it. So these things are called file descriptions. File descriptions. IONS. A file description contains a few things. It contains the path to the file that we are currently opening, or that is currently open for reading or writing or whatever. So a path to the file. It also contains the file offset. What's the file offset? Who remembers? Terminology question.
Where the file exists relative to like in the memory base.
That's a very good guess. That's an excellent guess, but that's not what it is.
Is
Yeah.
it the current point in the file?
Yes, that's what it is. So when you open a file,
It's what tell will tell.
it's what tell will tell you. It's what seek manipulates. Yeah. So when you open a file, there's an imaginary cursor in the file that sort of keeps track of where you are within the file, reading it or writing to it. The location of that cursor is the file offset. Okay. So the file offset is the location of the file stream's cursor, the file description's cursor. Right. And there's a few other things in here as well, besides the path and the file offset. There's some other stuff, control variables, things like that. Okay. This is all going to come back again next week when we talk about processes and fork and exec and things like that. But the point is, the reason I'm telling you all this now is that when you call the open function, this really low-level POSIX Unix standard file opening function called open, it returns a file descriptor. It doesn't return a file pointer, like a capital file stream pointer. It returns a file descriptor, which is the value in the left column in this table. So it opens the file, it creates a file description for the file, and for the file offset, the path, and everything. It creates a pointer that points to it. So like hello.txt, right? It creates a file descriptor for that pointer within the table, and then it returns the file descriptor, right? And so that's sort of your handle on the file. It's a little number that represents the file. Okay.
So in there, what does fopen return? Does it just return the pointer instead of the file descriptor?
fopen returns a pointer to like an internal structure type. And so a capital file is usually a type
just
def for a
has
structure type,
everything.
and it has a file descriptor in it. You can actually, there are ways to extract file descriptors from file stream pointers. There's a function that does it. Yeah. Okay. Good. So I need to supply this function some arguments, though. Let's see if I remember what they are. I'm surely going to have to look at the man pages. The first one, I believe, is just a C string containing a path to the file, just like with fopen. So maybe I want to open this file called hello.txt within my working directory at the time I run the program, right? fopen takes 2 arguments. Open takes 3 arguments because it's a little more complicated. The second argument lets you specify sort of like config flags for what you want to use the file description for. And so maybe you want to be able to read from the file, or maybe you want to be able to write to the file. Maybe you want to specifically append to the file. Maybe you want to be able to create the file if it doesn't already exist as you're opening it. All of these things that you might want to be able to do with the file as you open it are configured via special flags. You're usually going to need to supply multiple flags, but you only get 1 argument to do it. And the way you sort of combine these flags to enable a lot of different features for your file description is by bitwise ORing them together. And so I'll show you what that means. But let's see if I can find the man pages for all these flags.
Like blocks it from use from other features.
There are file locks. Okay, let's see. ORD, where is it? I don't think it's in here. Linux man. Maybe it's just in the open page. Okay, here are some flags you can use. Okay, good. So, if you want to open a file for reading using this old school POSIX Unix standard open function, then for the second argument, for the flag that you would supply here, it's O underscore RD only. Is that what it is? RD only. It stands for read only. This lets you open the file description for reading, but not writing. This is akin to supplying like sort of quotation marks R for the second argument to fopen. It opens the file for reading, but not writing. If you want to open the file for writing, then you do WR only, I think. Yes, WR only. That stands for write only. It is possible to open a file for both reading and writing. To do that, the flag is RDWR, RDWR, read write. You can open files for reading and writing with fopen as well.
Is that R plus?
You would do something like R plus is read and write, but don't create the file if it doesn't already exist. There's also W plus, which is read and write, truncate, create the file if it doesn't already exist. There's also A plus, read and write, append, create the file if it doesn't already exist, right? So you can do these things with fopen as well, but here's how you do it with open, right? Let's say I want to open hello.txt for writing, only writing. I'd say O underscore WR only, right? Write only. Okay, by default, even if you open a file for writing, it will not create the file if it doesn't already exist. So this will open it for writing, and it will also, I think, specifically truncate it by default. But if the file already or doesn't already exist, so there is no file called hello.txt in my working directory, if I just use this as my second argument, then this open function call will fail because it can't create the file if it doesn't already exist without supplying an additional special flag.
Does it just crash?
It doesn't crash. I think it returns. My guess is that it returns -1 and sets error no. That's the Unix programmer in me says that's what it would do. You can read the man pages if you're curious. Okay, if you want it to be able to create a file that doesn't already exist, in the case for you're opening it for writing, you additionally have to supply a second flag. And to combine these flags, you use this bitwise OR operator, which is a single vertical bar. Okay, it looks like a logical OR operator, but it's technically a bitwise OR operator. It's doing something slightly different. I'll tell you what it's doing in a minute. And then on the other side of this bar, you can supply additional flags. And so the Linux man page for the open function lists all of these different flags that you have available to you. Here are the 3 that I just covered, but there's a bunch of others. This is the one, O underscore create, because I guess they couldn't be bothered to name it create. This is the one that you would use in addition to OWR only or ORDWR if you want to be able to open files for writing and create them if they don't already exist. So O underscore create. O underscore create. You would do something like that. Okay, what does this bitwise OR operator do? These flags, what they really are, I mean, they're constants, but what they really are basically integers, like they're numbers that you could, because they're numbers on a computer, you could write them in binary, and so they would be a string of zeros and ones. What this bitwise OR operator does is it looks at the bits of the flag on the left and the bits of the flag on the right, and for each pair of bits, like the first bit in the flag on the left and the first bit in the flag on the right, for their binary representations, it looks at both of them and it performs a bitwise OR between them, which is to say, if either of those bits are 1, then the resulting bit from this operation is also a 1. If neither of them are 1, if they're both 0, then the resulting bit from this operation is 0. So suppose O underscore WR only, suppose this flag, this constant, is really integer 1. If you were to write that in binary, maybe it's something like that, right? Suppose O underscore create is integer 2. If you were to write that in binary, it would look like that. Let me line these up, okay? The bitwise OR between these two things then, the OR between WR only and creat would be, so O underscore R WR only or O underscore creat. This would be 000000011. Between the last bits of both flags, at least one of them is a 1. So the logical OR between them is also a 1. And looking at the second to last bit, between both of them, at least one of them is a 1. So the second to last bit, and the result is a 1. And so this sort of combines these two flags as bit strings into one bit string that contains all of their features, right? And so that's how it lets you combine these things with a weird bitwise OR operator.
Guessing the only reason we don't add them is because some of them might set other flags.
Well, if you added them, suppose you tried to add the same flag to itself, then it would carry
Or if there's a
and get your
flag
weird
that
thing.
sets other flags.
Right. And there are also flags that already combine some of these flags and so on.
Yeah, that's what I meant.
Okay, yeah.
Then if you added that to itself, then it would have.
Yeah, weird stuff would happen. So yeah, so you always use this bitwise OR operator. Yeah, in modern day interfaces, we generally don't do stuff like this, but bitwise OR to combine like bit flags used to be very, very common. And this is a very old interface, so you still use it. Yeah. There's also, I think, a flag for truncate, O underscore trunc. I don't remember what happens if you don't supply this. Maybe it defaults to append, but let's open with O underscore trunc as well. Something like that, to truncate. Trunc stands for truncate. Open the file for writing, create it if it doesn't already exist, and if it does already exist, truncate its contents before we start, like erase its contents before we start writing to it. That's the second argument to open. There is a third argument to open. This third argument is only relevant if a file is going to be created potentially in the process of opening it, which is to say, if you don't supply O underscore creat, and so this open function call isn't capable of creating new files, then the third argument isn't even really relevant, right? I think you still have to supply it, but it's not really relevant. The third argument is of type mode T. Mode T, I think. Let me confirm. Should be mode T. Very good, mode T. Okay, this third argument, mode T, it stands for mode type, okay? It's used to represent file modes. A file mode is, again, basically a big bit string, like a number, but represented, you can represent it with a bunch of zeros and ones, like bits, that encodes basic information about like some of the metadata of the file, including the permissions of the file, such as who is allowed to read it, write it, execute it, right? Things like that. Most commonly, when you supply this third argument, the mode T, you're basically, for the file mode, you're just supplying permissions, right? So we are going to supply permissions here. And what that will do is if this file doesn't exist, it will create it because we supplied the ocreat flag, in our bitwise ORed flags for the second argument, and it will create it with the permissions specified in the third argument, right? And again, this is irrelevant if you're not creating a new file. So there are a couple of ways to sort of express mode T values. The simplest way is to use octal codes. We talked about octal codes a little bit when we were talking about file permissions in the shell a couple of weeks ago, but here's a very brief refresher. Suppose I have this octal code 0722 or something like that. The way that you would sort of interpret that, like extract permissions out of that to understand, looking at this code, what permissions about a file does it represent? The 0 is just part of the octal code. It's just octal code notation, so you ignore the first 0. The 7, one way of doing this is convert it to binary. A 7 in binary is 111, 111, right? The 2 converted to binary is 010. And then the next 2 converted to binary is 010, right? So if we were to convert these 3 digits each into 3 bit strings, we would get 111, 010, 010. You then interpret these bits as read, write, execute for the owning user, read, write, execute for the owning group, read, write, execute for all other users. These are all ones, which means the owning user has read permissions, write permissions, and execute permissions. This is 010, meaning other user, or the owning group, users in the owning group, but not necessarily the owning user, do not have read permissions, because it's a 0. They do have write permissions, but they do not have execute permissions. Oops, because that's a 0.
What would you use it for, like a global log or something?
What would you use this for? I have no idea what you use this for.
I said like a global log that you don't want other people to see the log in.
Maybe. Yeah, I don't know. I just made this up. 722. Yeah. This was out of nowhere. Okay. That's just an example. If you wanted to create a file, hello.txt, and you wanted these to be the permissions of the file, for the octal code, for the mode t value, you would supply 0722. That's what you would supply for the mode t value. Does that make sense? Okay. Okay, questions? Okay, I know this is a lot. Bear with me. Okay, this 0 is really important. It's really, really important. This 0, notice that like Vim is highlighting it in a special way. In C, if you write out an integer, like a number, and you start it with a 0, then what that means is that this number is expressed in octal form. That means this 7 should be interpreted as bitstring 111, this 2 should be interpreted as bitstring 010, this 2 should be interpreted as bitstring 010. And so you end up with a proper mode T value that sort of has bits that look like this, right? Question?
So why don't we need the 0 for like chmod?
For chmod?
Yeah.
I think you do.
I just use 777 if it works.
What is the bitstring representation of decimal 777?
Isn't it just expecting that in the first place?
I don't know. I don't think so. I think chmod accepts a mode T value as well. Linux Man 3.
It's probably just being smart.
It might be.
What you mean.
Yeah, it might be recognizing that you're messing up and it just fixes it for you. Let's see. chmod. It's also a mode T value. I mean, I've seen cases where it straight up doesn't work.
From string in the first place, so it's a problem.
No, the string is the path. The second is mode T, which is just an integer.
Oh, this is the C function.
Yeah, I don't know. That shouldn't work. I'll look into it for you, and I'll try to figure out why that was working. But in general, you should remember to put the 0 here. If you
I was thinking on the terminal.
if you don't put the 0 here, if I just write 722, then C will think that I'm trying to pass in the integer 722, like the decimal number 722. It will convert that to binary form, to a bit string, which looks nothing like this. It's just a completely different bit string. So it will give you bizarre file permissions. So don't forget this 0, right? It's telling C that this is an octal code. There are other weird little tricks like this for integer literals. Like if you put a 0x, then that means you're trying to express something in hexadecimal form. A 0 means octal form, nothing means decimal form, but these are all different. So remember that 0 for mode T values.
chmod is looking at the range that it's getting, and if it's outside
It could
that
be.
range.
It could be, yeah, handling that for you. I don't know. I'll look into it. Okay, I think that's it. Let's just compile and make sure it compiles. See if I did anything wrong. I need to actually pass it into close. When you want to close it, you just pass in the file descriptor. Okay, good. I remembered it. Good. Before I run this, actually, maybe I'll run it. I think it'll just create the empty file. I called it read. Let's rename it write, because I'm opening for writing. Write. Run. So I should have hello.txt. Notice it's highlighted in green. That's because it has executable permissions, because I supplied 0722, which says that the owning user should have executable permissions, right? Let's look at it though. Hello.txt. Okay, notice we expected the owning group to have write permissions, and we expected other users to have write permissions. Why don't they? Does anybody know? When you create files in a Starnix system, there's something like sort of in the environment under the hood that modifies permissions of those files by default as they're created. What am I talking about?
So it applies that while you're doing it.
It applies it to open as well.
That
Yeah.
mask.
Yeah, it's the umask. It's the umask. Okay, who remembers what the umask is? Okay, see some hands, that's good. So refresher, in every Starnix system, at any given point in time, in every process, there's something called a umask. There is a shell command called umask that lets you view your current umask. It also lets you change your current umask. So I could say umask 0777 to change my umask to 777. I'm not going to do that. You get the point. If I run umask, you'll see that my current umask is 0022. Again, the first 0 is just saying this is an octal form. The umask is really 022. Okay, what this means, the 0 corresponds to no permissions. The 2s correspond to write permissions for the owning group and other users. But specifically, what the umask does is anytime you create a file and you say, I want to create a file with these permissions, whatever those permissions are, it will strip away the permissions specified by the umask. And so that's why it's called a mask. It masks out or subtracts away permissions. So if you try to create a file where the owning group and other users have write permissions, the umask will take away those permissions if your umask has the right bits to do that, right? My umask is 022, which means it strips away write permissions for the owning group and other users. So when I run ls-l, we see that my new file doesn't have write permissions because my umask stripped it away. Does that make sense? Okay. Suppose we want to sort of fix this, so to speak. Suppose in my program, write.c, I want to create this file hello.txt, but I actually really want other users and the owning group to have write permissions. Knowing that the umask will strip away those permissions, I have two options. Option number 1 is after I've created the file and after I've finished closing it, I can then go back and modify the permissions. There's a command that we talked about, a shell command called chmod, stands for change mode. It lets you do this. Yep.
Yeah, so chmod interprets all decimal as octal.
It interprets all decimal as octal. Oh, that's interesting. I wonder how it does that. I don't know how it does that. I don't know. I'll research this. Okay, but either way, there's this chmod shell command. We talked about this a couple weeks ago. Stands for change mode. Lets you change the permission bits of files. But suppose you want to do this from within a C program rather than within your shell, right? As it turns out, there is a chmod function in C that you can call that lets you change the file permissions of files. I think it's actually part of a different header file. I think it's sys/stat.h, which we'll use this more later today. So we include sys/stat.h and then call the change mod function. I think we just looked at this. Here it is. It takes two arguments, the file path to the file whose permissions you want to change, and then another mode t value. So I could change the permissions of hello.txt to permission 0722. So first I tried to open it and create it with those permissions. But if the umask stripped away some of those permissions, after we close it, we force change its permissions back to exactly what we wanted them to be, right? So I think that should work. Let's make sure. Okay, there it is. Our write permissions are there. Questions so far? Okay. There is another solution besides using change mod. And this other solution also works slightly differently. But the other solution is to modify your umask. My umask is currently 0022, at least in my shell. As it turns out, every single process gets its own umask. And the umask of a process is inherited from its parent process. So what that means is suppose I'm in my shell. Right? I'm in my shell. My shell has a umask because my shell is running in a process and every process gets a umask. This is my shell's umask. Suppose I run my program in my shell, ./a.out. I tell my shell to execute this program called a.out in my working directory. It will then create a new process. It'll spin up, it'll fork a new process to execute a.out, and that new process will inherit my shell's umask. So that's to say this, when my program starts, its umask will be the same as my shell's umask, 0022. If I want my program to have a different umask, I then have two options. Number 1, I can change my shell's umask before executing the program. You can use the umask function to do this, or the umask shell command. I could say umask 0000. That would change my shell's umask, and then I could run my program. But a better option, because you often don't want to change your umask for your entire shell, a better option is to change your umask strictly within the program, like within your C program, using C code. Just as there is a umask shell command that changes your shell process's current umask, there is a umask C function that changes your C program's current umask. So there's this function called umask, you call it, you supply a mode t value, it's like an octal code, maybe 0000. This changes my current processes, like this C program's processes umask to 0000, meaning don't strip any permissions away from newly created files.
Now it's what you see is what you get.
Now what you see is what you get, right? When I create a file and I say this is what I want the permissions to be, that's what the permissions will be. The UMask isn't going to strip away certain permissions because I've basically disabled the UMask here. Okay. I think UMask is also supplied by sys/stat.h. Can I confirm? UMask, UMask Linux man 3P. There it is, sys/stat.h. Mode T. It looks like it returns a mode T as well. I don't know what it's returning. You can look it up if you want.
The current UMask maybe?
Could be. That would make sense. I don't know.
If you supply null, I don't give you what it is.
Oh, okay. Okay, there we go. Those are your two solutions. Change your UMask before you start creating files. That lets you control the permissions a little bit more finely. Or create the files and then change their permissions, like force change them with chmod, which isn't sort of restricted by the current UMask. It just changes the permissions to whatever you specify. Of course, change mod, if you just use it in this context, it will also change the permissions of the file if it already exists. So suppose I run this program, this file hello.txt already exists. I'm trying to open it. Maybe I don't even want to create it because it already exists, and so I don't want to specify new permissions for it. Change mod will force change its permissions anyways. Whereas creating files using open and changing your, specifying your UMask accordingly would only create new files with specified permissions rather than changing the permissions of existing files. So they are slightly different, but both would work. You should, in general, be very careful when doing things like this. In fact, I generally don't recommend setting your UMask to 0. The UMask is an intended security feature. It prevents you from accidentally creating files that have too many permissions available, that will allow too many people to access these files, people who don't need to access the files. Disabling your UMask, sure, it lets you specify whatever permissions you want, but don't forget to re-enable the UMask at some point when you're done creating files that need to have very, sort of liberal permissions, right? Otherwise, if you set the UMask to 0 at the beginning of your program and you forget to ever change it back, then every file your program ever creates will sort of have maximal permissions of whatever you specify, even if some of them should be stripped away. So just be really careful. Just understand what you're doing.
Returns is what it was before you changed it.
I think maybe it is. I mean, we can look. Return value. The file permission bits and the value returned by UMask shall be the previous value of the file mode.
So you can make a backup.
So you can revert it. So you could do something like mode T old UMask gets UMask 0000. This would change the UMask to 0, and it would record the previous UMask in this variable old UMask. And then when you're done creating files, maybe down here, then you can call UMask again, pass in the old UMask to sort of revert it back to what it was. Yeah. That's probably how you do that. Okay, just be careful with that. You will probably need to do things like this for assignment 2. You don't need to set the UMask to 0. If you're careful on assignment 2, there's a very specific thing you can set your UMask to so that everything just kind of works from there. And you never need to use things like chmod. Okay. UMask or file permission bits and octal codes or any of these weird constant flags or bitwise OR operators. Yeah. Yep.
So the UMask is only within the context of the running application. So if you change the UMask and run another process that after you write a file in that amount of time, it wouldn't be applied after the change UMask.
Correct.
Unless you spun it up from within.
Unless you spun it up from within. Yeah. So every process has its own UMask. When a process creates a new process, which usually happens when shells execute programs, the process that they create, called the child process, inherits the UMask from the parent. But it gets its own copy of it. So then if you modify the child process's UMask, it doesn't modify the parents, but also vice versa. It definitely doesn't modify sibling processes. Yeah. Yeah, we'll talk more about processes next week and all the things that they have inside them, what's inherited, what isn't. But yeah. Okay, other questions? Okay, all right. Good, so I've taught you how to open a file and close a file. Let's actually use it for certain purposes. Okay, so we've got read, we've got write, we've got lseek. These are the ones that I want to cover. Read Linux Man 3. Okay. Good. Read. So, slides. Okay, the read function, which is provided by unistd.h, so it's a good thing that I included it. The read function takes 3 arguments. The first is the file descriptor. I don't know why it's called flides. I think there's some weird historical reason for this. I knew at one point I knew the reason, but I don't remember. File D's? File descriptor, maybe? Something like that. Files? So that would be your file descriptor, the thing that I stored in a variable called fd. And so that's the way that all of these functions handle the file, is just with this integer file descriptor. So I'm going to call the read function. If I had opened this file for reading, I could do this. You would pass in the file descriptor, and then there's this void buffer. Let me actually demonstrate this, because then I think it'll make more sense. In order to demonstrate this, I'll need to open a file for reading instead of writing. So let me create a read.c. Let's include fcontrol.h and unistandard.h. And I don't think I'll need sysstat for now, at least. Let's create our file descriptor. Let's call open. Let's open data.txt, something like that. Let's open for reading, so rd only. I don't need rcreat, because we don't want to create the file if it doesn't exist, because we're just trying to read an existing file. And I don't need otrunc, because I don't want to truncate the file. For the third argument, I think it's ignored anyways. I'm just going to supply 0. Can maybe even leave it out. I don't remember. Okay, I'm going to not forget to close it. That's important. Okay, so suppose I want to read some data from this file. The read function is used to read like bytes of data from a file. Like not strictly text, but just like a stream of bytes. And like that's it. It doesn't do anything fancy with like C strings. It doesn't even assume that the data that it's reading is in fact a string. And so if you're trying to read text data from a text file, you can do this with the read function, but you have to like handle a lot of the C string stuff yourself. You basically would use this to like read an array of characters. You would then have to manually null terminate that array, because like the read function won't null terminate it for you. Unlike getLine and fgetS, which will null terminate it for you, read wouldn't. But the really cool thing about read is that it doesn't just read text, it just reads a byte, an array of bytes or something like that. Read and write, these functions can be used to like write as like in binary representation. You can write the bytes of like entire structures or arrays of structures and just serialize it to binary straight in some file. And then you could read those bytes using the read function straight from the file back into an array of structures. So I'm gonna, maybe for my demonstration, I'll actually do a write example and a read example. And let's say we have a structure type called person. And maybe every person, let's keep things simple, every person has an age, and maybe every person has a favorite number. Okay, something like that. Maybe I have a file. Let's call it, I don't want to call it data.txt because it's going to be storing binary data. Let's call it data.dat. DAT is a common extension for just like binary data files. Okay, so we've got data.dat. Suppose this file contains like the bytes of a person structure. Maybe previously we ran a program that had an identical structure type. It created a person, and it used the write function to write that person's bytes into data.dat, which we'll do that in a second. Suppose I then want to open that file and read those bytes and to sort of load this person from the file. I have to create my person, right? Struct person p, and then I want to read from the file, right? That's the first argument, it's the file descriptor. The second argument is a void pointer called buff, which stands for buffer. A void pointer is just a generic kind of pointer. It's a pointer that points to some space in memory where we want to store the bytes that we read from the file. I want to read a bunch of bytes from this file and store it in like the structure called P, the person structure called P. So I might pass the address of P as the second argument. You can pass any kind of pointer you want as a void pointer. Void pointers are like very generic kinds of pointers. Okay, that's the power of this stuff. You can read and write arbitrary data. It doesn't have to be text. Okay, the last argument is, I believe, the number of bytes that you want to read, right? Size t, number of bytes. Suppose a person has 4 bytes in it. It's probably going to be more like 12 or something, but suppose a person has 4 bytes of memory needed to like store all of its data. Then I would want to read 4 bytes here. all of the bytes in the file that store the person. Suppose a person has 12 bytes, then I want to read 12. So maybe the number of bytes I want to read is the size of a struct person, right? Or equivalently, the size of P. This would do the same thing. Okay, maybe I'll say size of struct person. That's more conventional. Yes. Hopefully the writing system and the reading system, things work the same. Okay, that'll be important. Okay, the return value. So those are the arguments. What's the return value? I think it returns the number of bytes successfully read. Okay, so when you call read, and this is sort of an annoying thing about read and write in some of these old style file IO functions, when you here's how much or how many bytes I want to read. Here's where I want to store those bytes as I read them from the file. Here's the file that I want to read from. But it doesn't always actually read that many bytes. There's a lot of reasons that it might fail to read the number of bytes that you specify. It could be that it like hits the end of the file, so there's no more bytes to read. You know, maybe I'm trying to read 100 bytes from the file, but this bytes only has 50 bytes, or this file only has 50 bytes in it. So that's one reason it could fail. But it could also fail for other complicated reasons. A signal could be sent to my process that like interrupts the read and then it terminates midway or something like that. Weird things can happen. It's not an atomic operation, which means it might not actually successfuli read this many bytes. It will then return the number of bytes that it did successfully read. And so you usually are going to want to store that value in a variable. Its type is signed size type, size t. I'm going to call it nread for like number of bytes successfully read. In practice, what you'd want to do is after calling the read function, you would want to check, is this number equal to this number? Did we successfully read all of the bytes that we were trying to read? And if the answer is no, if this number is less than this number, then you want to call the read function again to try to read the remaining bytes. Or you want to like move your pointer back and like try to read the entire file again or something like that. So we're reading like parts of a buffer at a time potentially. In practice, this is what you'd want to do. You would usually do this with like a loop. Like while the number of bytes, total number of bytes read is less than the total number of bytes we're trying to read, keep reading more bytes or something like that. But for the sake of time and simplicity, I'm just going to assume that it successfully reads all of the bytes because it usually does for small file reads like this. The reason it's a signed size type is that it can return negative values. I think it returns a -1 on error and then sets error no accordingly. Okay. If you want to do error handling, you can look into the man pages. Okay. So we've read the file or the person from the file, then we close the file, and then maybe in the end I just want to print some information about this person to the terminal. Printf, the person is blank years old, and their favorite number, fave number is %lf, 0.2lf, \n, p.age, p.favorite number, something like that. Okay. Of course, for this to work, this file must exist, data.dat, and it must contain like the binary representation of a person structure. So let's write another program to create data.dat with that binary representation. So the first thing I'm going to do is copy this person structure type, because I need to create another program that will write this file. So I'm going to copy the structure type exactly. Now I'm going to go into write.c, I'm going to paste it. And I'm going to update this program to create a person structure and write it to the file. So this will be the saving program, read.c will be the loading program, basically. Okay, let's modify this a bit. We're now going to open data.dat instead of data.txt. We do want to open it for writing. We'll create it if it doesn't exist. We'll truncate it as we create it if it does exist, or as we open it if it does exist. And sure, we'll keep the umask stuff the same, why not? Maybe I don't want it to be executable. So maybe I say 622. That's read, write, but not execute. Maybe even 600. Okay, something like that. Good. In the middle, I've opened the file. I have my file descriptor. Before I close it, I want to create a person structure, and I want to write that person structure's bytes to the file. So first, I create a person struct person p. I need to give P some data to save into the file, an age and a favorite number. Okay, how old should P be?
12.
12? 12-year-old. What's this 12-year-old's favorite number? 12. That's how old they are. Of course, that's their favorite number. Okay, we've created our person. Maybe we want to like save them into this data file. We want to write them into this data file. So of course we call the write function. Its syntax is probably going to look familiar. Oops. Write Linux man 3. Okay. The first argument is files, the file descriptor. The second argument is a void pointer. The third argument is size t and byte. The return type is s size t. Notice this is identical to the interface of read, right? Of course, the interpretation is slightly different. So the first argument is our file descriptor, so the file that we want to write to. The second argument is a void pointer. In this case, instead of being the address of a buffer or an address of a structure or an array or whatever in which we want to store the read data, in this case, it is an address to the buffer from which we want to pull data to write it into the file. I want to take the bytes inside this person P, and I want to write those bytes into the file. So I take the address of P. That would be that buffer, that void pointer buffer argument. The address of the bytes we want to write. Okay. The third argument is the number of bytes that we want to write. So it's going to start at this address, which is basically the base address of P, and it's going to start pulling bytes out of this person one at a time until it has pulled the number of bytes that we specify, and then it will write all of those bytes to the file. Again, if a person has 12 bytes, then I want to write 12 bytes to the file. I'm trying to save the entire person. And so again, I would use size of struct person as our third argument, something like that. Once again, just like with read, write can fail to actually write the number of bytes that you request. It could just write 3 bytes and then kind of terminate in the middle because it gets interrupted for whatever reason. And so once again, it will return to you the number of bytes that it successfully wrote as an s size t value. And again, I think it returns -1 on failure. And so you can check if it's -1. And once again, to be robust, the way we normally use this function is keep running it in a loop until the total number of bytes written matches the total number of bytes you're trying to write. And you also have to sort of update your base address as you go. It's a little complicated. But again, I'm just going to assume that it's going to work because it generally does for small writes. And so that's probably good enough for now. Okay, we close it. Update our UMask, sure. Let's see if this works. I've surely made some mistakes. Okay, it compiles. It runs. We've now got data.dat. The permission should be read write for me, nothing for anybody else. And then we've got read.c, which is going to try to open that file and read the bytes that we just wrote into the file and read them into this new person structure in this other program. Let's see if it works. GCC read.c. What'd I mess up? I guess I need to include studio.h to use printf. Ah, I didn't mess up. There it is. Okay, questions or comments? This is read write. Yeah.
Why would somebody prefer a non-atomic function that does literally the same thing?
Why are you saying why would they prefer read over like fread or something like that?
You have to babysit it.
I actually don't remember if fread is atomic. Fread Linux man 3.
Fread, you can't just write the whole structure.
Let's see. Size t function f reason member each size while storing them as a function f reason members. Each size. I think it is. I think it will always, like it encodes the loop inside it. Yeah, why would you want to do that? I don't know. Complicated reasons probably. Something that's not obvious to me. Yeah, most of the time when people use read and write, they use it in a loop until it's read or written the number of bytes you need. Basically, your question is, why isn't that loop just inside the function? Is that what you're asking? Sometimes you just want finer control. A lot of this stuff in the POSIX Unix standard is really low level. That gives the programmer like maximal control over how things are done. And so maybe if you want to try to read 8 bytes, but it only successfully reads 3 bytes, maybe you, the programmer, like in the code, you want your program to be able to diagnose why it failed, detect the failure and diagnose why. Maybe the file doesn't actually have 8 full bytes after the file offset. Maybe there are only 3 bytes remaining. So maybe it fails because it hits like the end of file, And maybe you want to be able to detect those specific kinds of errors and respond appropriately or something like that. Yeah. It just gives you more control, but it also makes it more complicated to use. Yeah.
That means you're writing it, it's not truncating, which you only have until the end of the file.
Writing and not truncating, like appending. Okay. Other questions? Okay. The last of these functions to talk about is lseek, but let's take a break. We'll take a 10-minute break, then we'll talk about seeking, and then we'll move on to bigger, better things.